Okay, we're going to revisit maxima and minima problems. We already looked at them once this year when we were talking about quadratics. And we said the maximum or the minimum was the vertex of the quadratic. Because now that we've got calculus, we're not limited to quadratics. We could have any function really, but it's still the same idea. We just want to find where's a maximum or where's a minimum. Now we don't actually have to draw the graph, because we know that's going to happen when the first derivative is equal to 0. So we can use the calculus to find it without actually having to draw the graph up, which I know would disappoint you, because I know how you love drawing your graphs. But, you know, it'll save us a little bit of time. So the idea, so we've got some word problem that we're going to solve. You're going to reduce the word problem down, and it's usually going to be to a set of two equations. One of those equations, you'll read through the problem, and you'll be asked to find the maximum of this, or find the minimum of that. So that'll give away, okay, that's one equation I've got to work out. Then there'll usually be some sort of linking information in there. So it might be the amount of material you've got to use. You know, oh, the surface area has to equal this, or something like that. So once you've done that, we want to try and rewrite the one we're trying to maximise and minimise in terms of one pronumeral. And that's where we'll use the linking information so we can rewrite it. A bit like parametrics. And then we go and use our calculus to go and solve our problem. So alright, here's a typical problem. I'm sure you've experienced it yourself. You've got a rope 36 metres long and you think, what the heck am I going to do with this piece of rope? And you decide, I know what I'll do with it. I'll cut it into two pieces. As I say, common problem. Now your first piece of rope, you go, hey, let's form a square. And you know what would be fun? The other piece of rope, I'm going to make it a rectangle, but not just any rectangle. It's going to be a rectangle where one of the sides is the same length as the square I just made. Now we want to do it so that the area inside our rope is going to be a maximum. I still find pictures useful to try and visualise the problem. So there's my two bits of rope that I've bent. One forms a square, one forms a rectangle. I've got to work out some dimensions. Creatively, I've called the side of the square S. I don't know how I come up with these things, but there you go. Which means our rectangle will have one side S, and I'll call the other side R for rectangle. All right. We're trying to get two equations here. One is what we're trying to maximise or minimise. And if we read through our problem, there it is, right at the end. We want to find the sum of the areas is to be a maximum. So we'll come up with a formula for the sum of the areas. Well, area of the square will be S squared. Area of the rectangle will be RS. I've got one equation. The other equation is some piece of linking information. How much material have we got to use? That sort of thing. That actually is the first sentence. We know the rope is 36 metres long, which means basically the perimeter of these two shapes, because that's my rope, must equal 36. So 6S and 2R will be 36. Now, its area I'm trying to minimise and maximise. On the right-hand side, it's in terms of two variables, R and S. But I now have some linking information which will allow me to eliminate one of the pronumerals. As I say, a bit like parametrics. We want to eliminate a parameter. It's our choice which one we get rid of, the R or the S. Which one do you think would be more logical to get rid of? Yeah. I would too, because there's only one R there to substitute into. So let's rearrange the second one to make R the subject. And we end up with R is 18 minus 3S. Substitute it into my area formula. And I now have a formula for area just in terms of the side of the square. Make it look a little bit neater. Now, it's at this point I've actually got a choice. Because you'll notice we've ended up with a quadratic. This question has not actually said, go and use calculus. It has simply said, find the length of the square. So I could now use quadratic theory to go and do it. We just want the dimensions, not the area, so we're looking for the axis of symmetry. So I could go minus b on 2a, that'll give me the S value. But let's just pretend we didn't know that. Let's use the calculus, otherwise it becomes a bit of a silly example. So there's A. Going to need my first derivative, dA ds. And to confirm that it'll end up being we were wanting a minimum or a maximum. It was a maximum, wasn't it? We'll need our second derivative. Stationary points will occur. Now I'm not going to draw the graph, but I still want to locate that stationary point. And we get S is 9 on 2. Now let's just confirm that that does give me the maximum. Second derivative is negative, concave down. Therefore, here I am, up at the top. So yes, when S is 9 on 2, which is the length of the square, the area is a maximum. Notice, I didn't bother finding the area. The question didn't ask for it, so I'm not going to waste time. The question simply said, what's the length of the square? But the interesting thing is this. If the square is 4.5 metres, what's the length of my rectangle? Remember, we had 36 metres all up. The square, 4.5. So I've got 4 of those in the square. So that's 18. Leaves me with 18 for the rectangle. I've got 2 sides of 4.5. That's 9. Leaves me with 9. What's the length of the rectangle? It's a square as well. And you will find with these, what we call optimisation problems, where we're trying to maximise, minimise, very often the perfect shape will give the best solution. So, when we're talking about maximising rectangles, it'll turn out to be a square. If I was talking about a solid, it would be a cube. But the perfect shape often turns out to be the solution that we end up looking for. Alright, let's do one which doesn't turn out to be a quadratic, so I've got no choice. We have to use the calculus for this. We're going to make a bucket. Now our bucket's a very special bucket. It's going to be a cylinder, unlike a normal bucket, which if you think sort of tapers a bit. And we want to hold the maximum amount of liquid in our bucket. The surface area of the bucket, wow, that's fortunate. It happens to be an exact multiple of pi. Phew. 12 pi units squared. And amazingly, we're going to make this bucket and there's going to be absolutely no wastage whatsoever. We're going to use every single piece of material. Of course, in reality, that can't happen. And actually, when you do these sorts of problems, I suppose when you get more to university level of optimisation, you have to take into account all these extra bits of, oh yes, there's going to be wastage and other equations come into play as well. We're looking at a simplified model like this. So there's my bucket. It is indeed a cylinder. Radius, I've conveniently called R, and height, yes, very creatively, H. Looking for 2 equations. One is what we're trying to maximise or minimise. Now, where is it? Yes, I saw it. Yeah. Hold the largest volume. Volume of a cylinder, pi r squared H. Okay, so there's one formula. Some sort of linking information, how much material have we got to use, that sort of thing. And there it is, total surface area. Surface area of my bucket. Say it again. 2 pi r h?
Plus 2 pi r squared.
Close. 1 pi r squared. Because if you make your bucket with 2 pi r squared, very hard to pour the liquid into the bucket. So the top's going to need to be open for this one. So we'll have one for the bottom, but not for the top. Alrighty. Well, at this stage, volume is in terms of 2 variables. We're either going to make H or R the subject. I think I know which one's going to be easier. Which one will we go for? H sounds like a plan. But also, look at this. Wasn't that so lucky the surface area was multiply? Pi goes and everything, it'll cancel. Wow. Sometimes the real world is very good to us. Make H the subject. We get 12 minus R squared over 2R. Substitute into volume. I might expand that out. I think it'll be easier to differentiate. There we go. We end up with a cubic. So if I was to draw this graph, we know we've got a cubic. It looks like it's going to be one of those ones where we've got a maximum turning point, we've got a minimum turning point. The one we're looking for, of course, is the maximum turning point, because we want to get the most possible liquid into the bucket that we can. So let's find our derivatives. There's volume. Remember, pi is a constant. It's r that we're differentiating with respect to. 6 pi minus 3 on 2 pi r squared. Second derivative, minus 3 pi r. Stationary points occur when dVdr is 0. Solving that, I get two possibilities. One is going to give me a maximum. One will give me a minimum. Logically, which one should I pick? Which one? Okay, yes, you are correct. Logically, I should pick the maximum because that's the one we're trying to find. But logically, which one, either r equals positive 2 or r equals negative 2, should I pick? Why?
Because it's bigger. Yeah.
Because it's bigger? No. That's not the reason why. Why would you pick positive 2 rather than negative 2? Yeah, it'd be pretty hard to build that bucket with a negative 2 radius. So I'm not going to worry about negative 2. I'm going to test the positive 2. And sure enough, I get that the second derivative is negative, which confirms it is a maximum. Now, in this case, I do have to go and find things because it did ask me for several pieces of information. I know the radius is 2. When I substitute that in, I get that the height is 2. So what have I got? I've got a short, fat bucket, haven't I? And when we work out the volume turns out to be 8 pi. So it's 8 pi units cubed when the radius and the height, but notice again, the perfect solution there was when the radius and the height was the same amount. So. Alrighty, let's play with our maximum and minimum problems.